Is it okay? Okay, no. I don't understand your hand gesture. Okay, I'm waiting. Just hit OK here. Okay. Okay, yeah. So today, the second speaker is Ching. He will talk about this amazing paper that I'm really proud of. So this was published in DRAMSec, DRAM security workshop earlier this year. That was collocated with one of the top conferences, ISCA. And this paper explains and analyzes the industrial state of the art in RowHammer defenses called a mechanism called PRAC that Chen will explain in a little bit in the presentation. So our speaker is a second-year master's student in computer science department of ETH Zurich, and his main interests are not in RowHammer, surprisingly. They are in data management systems, software engineering, and programming languages. And he also got his bachelor's degree earlier from ETH Zurich in computer science. So he's going to be presenting remotely. So I hope the slides are clear to you. And yeah, I guess we will still use these microphones to ask our questions to him. So can you speak so that we can test the audio here, Cheng?
Can you hear me?
Maybe I need to increase the audio here.
Maybe also change the view.
There's a view button on the top right.
Yes. Multi-speaker, maybe? Okay.
It's fine, I guess.
Yeah, it's fine. But I cannot hear him. So could you go to audio settings? Maybe it's put in the speaker to MacBook.
Correct.
It's correct. Can we test here? Maybe I can increase it a little bit. It's clear from back. Is it too much? Okay.
Chen, can you hear us?
Yeah.
Can you speak from the?
Can you hear me now?
Okay.
Yeah.
Okay, perfect.
Yeah.
Floor is yours.
Okay. Thank you for introducing me. So hello everyone, my name is Chen, and I'm going to present a paper which is about understanding the security benefits and overheads of emerging industry solutions to DRAM redisturbance. So this is the outline of my presentation. Let's start with introduction and motivation. Yeah, I think most of you should be familiar with DRAM, but let's do a quick recap. So DRAM, or dynamic random access memory, is a type of memory which is widely used in computers and electric devices. It's used to store the data temporarily, and the word dynamic comes from the fact that this type of memory relies on continuous refreshing to maintain the data. And each memory cell in DRAM consists of capacitor and transistor. Capacitor stores the data in the form of electric charge. If it's charged, it represents the bit stored in it is 1. If not, then it's 0. And transistor controls the access to capacitor. The problem is the charge leaks slowly, and refresh operations just recharge the capacitor if the stored bit is 1 or keep capacitor uncharged otherwise. And DRAM is organized in a matrix of cells where data in each cell is accessed by activating specific rows and columns. The capacitor in each cell is quite small and volatile to electric noise. Therefore, activating a particular row in DRAM causes electrical disturbance, which can disturb nearby unaccessed rows of memory cells. It could lead to bit flips where the data stored in those adjacent rows unintentionally changed. As modern DRAM packs more cells into smaller physical space to increase storage capacity, and each memory cell becomes smaller, the read disturbance problem intensifies. A famous example of read disturbance problem is RowHammer. The attacker activates or hammers aggressor row repeatedly, and electrical disturbance to victim rows keeps growing until bit flips occur. Another example is row press. Unlike RowHammer, instead of activating a row repeatedly, row press just keep a row to be continuously activated until bit flips in nearby victim rows occur. Even more concerning, RowHammer and row press can be combined for an even greater effect. As shown in this figure, an attacker can press the first row while hammering the third row. The combined effect of RowHammer and row press amplifies the disturbance, making it easier and faster to induce bit flips in the victim row. But today we will just focus on RowHammer-like attacks. So the question is, how can we solve read disturbance problem to maintain memory isolation? Since the read disturbance problem stems from the inherent properties of DRAM, without changing the fundamental structure, a straightforward solution is to preventively refresh potential victim rows before bit flips occur. But how to realize this idea? So here is the executive summary of my presentation. As mentioned, the problem that needs to be solved is DRAM suffers from read disturbance, which breaks memory isolation. Based on this demand, there is an existing industry solution called PRAC. This mechanism is able to keep track of row activation counts and perform preventive refreshes when necessary. So the goal of this paper is to evaluate PRAC's benefits and overheads. As the most important contribution, authors provide the first rigorous security, performance, energy, and the cost analysis of PRAC. And the outcome shows, although PRAC is highly effective in mitigating RowHammer-like attacks, it also causes significant overhead at the same time. And PRAC underperforms other state-of-the-art read disturbance mitigation mechanisms in modern DRAM chips. However, in future chips, PRAC shows a great potential. We will see later why it is so. Now let's discuss the industry solution PRAC in more details. So as mentioned, a state-of-the-art read disturbance mitigation method is refresh management, or RFM in short, and per-row activation counting, or PRAC, which are described in DDR5 specification. RFM is basically a DRAM command that provides DRAM chip with a time window, for example, around 200 nanoseconds, to perform preventive refreshes. And PRAC maintains an activation counter per row to accurately identify when a preventive refresh is needed. Each time when a row is closed after activation, the counter of this row is incremented. Recall that when an activated row is closed, it needs to be pre-charged before another row in the same bank can be activated. The required time for this process is called row pre-charge time. And row active time, or TIS, is the time a row needs to remain open for a read or write operation. Row cycle time, or TRC, is the sum of TRP and TIS. So as we introduce a new mechanism of PRAC, and we need to do stuff like incrementing the counter, which brings additional processing overhead, such timing parameters of DRAM, including TRP or TRC, need to be increased as well due to extra time required for those operations. So before I show how RFM and PRAC works exactly, maybe we need to get familiar with some basic definitions. Firstly, the term NRH represents the minimum hammer or activation count to induce the first bit flip. MBO is a back-off threshold. Typically, it's a fraction of NIH, for example, 70% or 80% and so on. The back-off signal is asserted by DRAM chip if a DRAM row's activation count reaches the back-off threshold MBO. After receiving the back-off signal, memory controller issues RFM command within predefined time window. So let's take a look at this example. Suppose NIH is equal to 3 and MBO is 100% NIH, which is 3 as well. Initially, every row's counter is set to 0. Firstly, let's say the second row is activated and closed. Its counter is incremented to 1. Then the first row is activated and its counter is incremented to 1 as well. Then we keep activating and closing the second row until its counter reaches the threshold MBO. Now, so DRAM chip monitors the counter of all rows, and now it detects counter of the second row reaches the back-off threshold. Then DRAM chip asserts a back-off signal and is sent to memory controller. After memory controller receives the back-off signal, it issues a RFM command to DRAM chip. And after receiving RFM command, DRAM chip checks which row has the maximum counter. So in our case, it's the second row. Then it refreshes potential victim rows of the target row, which are the first and the third row. And finally, it resets the counter to 0 again. And before we move on to the next point, I have a few additional remarks. Firstly, DRAM chip is responsible for monitoring row activation counters and performing preventive refreshes when necessary. Additionally, issuing a RFM command is not instantaneous. During the predefined time window, memory controller can continue to serve normal requests, such as reads and writes, meaning that more row activations are possible even after a back-off signal has already been asserted. And in our previous example, only one RFM command is issued for each back-off signal. However, in practice, it's also possible to issue multiple RFM commands. The number of RFM commands issued is referred to as the term nref. Also importantly, PRAC always refreshes the potential victim rows of the row with the highest activation count during each RFM command. Finally, DRAM chip cannot assert a new backup signal until it receives a specific number of activate commands. And it's called a delay period, and it ensures that preventive refreshes are not performed too frequently. Besides, there are also different implementations of PRAC. The first one is PRAC-N. This is the most typical implementation of PRAC, and it's exactly the same as I have presented in the previous example. So the N here stands for how many RFM commands are issued when receiving a backup signal. So in our example, we basically have a PRAC-1 system. The second one is periodic RFM, or PRFM in short. In this implementation, there is no backup signal. Instead of keeping track of row activations, we just monitor the total number of activations to the whole bank. The memory controller periodically issues RFM commands when this number reaches a predefined threshold value. And here is an example of PRFM. As you can see, memory controller is responsible for monitoring total activations to the bank. If this value reaches threshold, then it issues RFM to DRAM chip. Once DRAM chip receives the RFM command, it performs preventive refresh. The next one is PRAC plus PRAC. It's just a combination of previous two implementations, which means RFM commands are issued when total number of activations to the bank reaches the threshold or the controller receives backup signal from DRAM chip. The last one is called PRAC optimistic. It's actually same as PRAC 4, but without increasing timing parameters, including TRP and TRC. So PRAC optimistic is basically a hypothetical model, and it assumes PRAC can also work without increasing timing parameters. Okay, let's come to evaluation. I think now most of you should believe that PRAC indeed improves the security, but the question is, how secure is it? And as you may already notice, PRAC causes some overhead. So what's the impact on performance, on energy consumption, and so on when deploying it? And as mentioned in executive summary, authors present a rigorous analysis of PRAC, which is also the most important contribution of this paper. Let's go through them one by one. So firstly, let's consider an adversarial access pattern called wave attack. The goal of this attack is to achieve the highest activation count for a given row. The key strategy of this attack mode is to overwhelm PRAC with using a number of decoy rows, which means attacker hammers a number of rows in a balanced way to distribute activations across all rows as much as possible. Secondly, it hammers the true target row while PRAC is overwhelmed by decoy rows. Here is an example of wave attack. So we still have 3 rows. And firstly, we hammer the first row, then the second row, then the third row, and we continue repeating this process. After several rounds, let's say the second row and the third row reaches MBO, which means DRAM chip accepts backup signal, memory controller issues RFM, and DRAM chip starts to refresh these 2 rows. So now attacker successfully let the DRAM chip be overwhelmed by dealing with these 2 decoy rows, which are not the true target of the attack. At this time, attacker gets back to the first row and hammer it. Since the counter of the first row is already near MBO, and after several activations, it's absolutely possible that its counter becomes over MBO. But as DRAM chip is still overwhelmed by decoy rows, it cannot get back to handle the first row in time, which could lead to bit flips. So here you can see the maximal activation count an aggressor row can reach before its victims are refreshed for PRFM. And in this figure, x-axis represents bank activation threshold that triggers RFM command, while the starting row set size at the beginning of the attack is color-coded. What we can observe here is for very low NIH values, such as 32, the RFM threshold needs to be configured to a very low value, as low as 4. This means in PRFM, ensuring security comes with a significant performance overhead, as it requires more frequent refreshes to maintain data integrity. And here is a figure of the maximal activation count an aggressor row can reach for PRAC N. The x-axis shows the backup threshold, and the number of RFM commands is color-coded. As you can see, PRAC N can achieve very high security, even for NIH value is equal to 20. To accomplish this, a configuration of PRAC 4, meaning 4 RFM commands per backup signal, and a backup threshold of 1 are required. And in following evaluations, PRAC is compared to 3 other mechanisms. The first one is graphing, which maintains row activation counters completely within processor chip. The second one is para. It takes another approach and does not maintain any counters. The last one is called Hydra. It maintains counters directly in DRAM chip, but also caches them in processor. Additionally, Table 1 provides an overview of the system configuration used by authors during the experiment. Now let's come to performance evaluation. In this figure, the x-axis shows different NIH values, while y-axis represents system performance in terms of weighted speed up, normalized to a baseline with no disturbance mitigation. The first noticeable trend is that as NIH values decrease, performance overhead increases across all mechanisms. This is because a lower NIH simply requires more frequent preventive refreshes, which naturally impacts the performance. For high NIH values, such as 1000, PRAC optimistic shows almost no performance loss since it does not increase timing parameters like TRP and TRC. In contrast, PRAC-N configurations like PRAC-4 still cause some performance loss at higher NIH values. Besides, graphene and Hydra obviously outperform PRAC when NIH is relatively high. As NIH value decreases from 1000 to 64, PRAC scales well, and between 128 and 64, PRAC begins to outperform Hydra and performs similarly to graphene. This is because PRAC can track aggressor role activations more accurately, allowing it to minimize unnecessary preventive refreshes. When the NIH value drops below 64, PRAC's overhead increases significantly. This is because PRAC needs to perform many more preventive refreshes, leading to a steeper performance decline. Also notably, PRAC optimistic outperforms all evaluated mitigation mechanisms between NIH values of 1000 and 64. Finally, in general, both PRFM and combination of PRFM and PRAC perform poorly. This is largely because PRFM tracks the total activations to a bank rather than each individual row, which leads to more frequent refreshes than all other mechanisms. And this figure presents the energy consumption of these mechanisms as NIH decreases, normalized to a baseline with no redisturbance mitigation. So firstly, DRAM energy overhead increases for all mechanisms as NIH values decrease, which is understandable since lower NIH values require more frequent refreshes. And as NIH decreases from 1000 to 20, the energy consumption of PRFM increases up to 4 times the baseline. PRAC optimistic 7 times and PRAC-4 13 times. Therefore, a significant portion of PRAC's DRAM energy is likely due to the increased timing parameters. Finally, graphene and Hydra outperform all PRAC implementations at all evaluated NIH values except for PRAC optimistic at NIH higher than 32. Finally, in this figure, we can observe the storage requirements of these mechanisms. So as NIH values decrease, the storage overhead of graphene increases significantly, while the storage overhead of all other mechanisms decreases. The primary reason is in graphene, all previously assessed rows are continuously monitored. Even if a row's counter is reset after refresh, the system still keeps track of that row. In contrast, Hydra and PRAC operate differently. Once a row's counter is reset after a preventive refresh, these mechanisms stop tracking that row, reducing the number of rows being monitored and therefore decreasing their storage overhead. Finally, PRFM incurs only minimal storage overhead across all NIH values, as it only needs to maintain 1 counter per bank. So previously, I presented the wave attack. Instead of trying to induce bit flips, attacker can also take advantage of PRAC to mount memory performance attacks by triggering many preventive actions. Authors of this paper simulated 60 4-core workload mixes with varying memory intensities, where 1 core maliciously hammers 8 rows in each of 4 banks. The results are presented in this table. We can observe that in general, the impact of this kind of attack on system performance increases as NIH values decrease. In some cases, the problem of performance degradation is extremely serious, with single applications experiencing up to 82% performance drop. Okay, so in conclusion, this paper introduces PRAC redisturbance mitigation mechanism and evaluates its benefits and overheads. On the positive side, PRAC effectively protects the system under wave attack, even at very low NIH values, such as 20, ensuring strong mitigation against RowHammer-like attacks. However, implementing PRAC also causes performance overhead due to the need to increase key timing parameters. In modern DRAM chips, which typically have high NIH values, PRAC tends to underperform state-of-the-art mitigation techniques like graphing and Hydra. For future DRAM chips, which are expected to have lower NIH values, PRAC-N is able to outperform those mechanisms. Finally, from a wide range of NIH from 1000 to 64, PRAC optimistic outperforms all other mechanisms, demonstrating that PRAC without increased timing parameters could have a great potential. Okay, now let's move on to the final part of my presentation. Firstly, I would like to analyze strengths of this paper. So I think the paradigm of PRAC is explained in a relatively simple way. That means authors focus more on introducing the high-level idea rather than design details. Even readers who do not have prior background in this field can understand it. Furthermore, the evaluation basically covers the most important aspects like security, performance, and the results are also well explained. Authors provide clear explanation for almost all evaluation outcomes. Additionally, PRAC is compared to other state-of-the-art mechanisms such that readers can easily figure out what are strengths and what are weaknesses of PRAC. What I especially appreciate about these evaluation figures is how they clearly illustrate the range of NIH values where PRAC excels and where its performance starts to falter. On the other hand, this paper doesn't really explain how graphing, para, and Hydra works. So it could be difficult for readers to interpret the evaluation results and understand how PRAC measures up against these alternatives. Besides, this paper mainly focuses on PRAC-N, while PRAC optimistic is only briefly mentioned in a single sentence. I quote this from the original paper. It says, PRAC optimistic, which is the same as the default PRAC configuration without any change in timing parameters. I think this leaves a significant gap in, in understanding for readers. One of the biggest questions that arises when I read this paper is related to how PRAC-N increases timing parameters to account for the extra time required to perform PRAC operations, but PRAC optimistic does not need to do that and it still works. Later on, I learned that PRAC optimistic is actually not a real implementation. It's basically just a hypothetical model. So maybe it could be a little bit confusing by only reading this sentence in the paper. Finally, in the security evaluation, authors only assesses how PRFM and PRAC-N perform under the wave attack. Although the goal of this paper is to evaluate PRAC, but I think instead of just saying PRAC is also is able to ensure security at a very low NIH level, authors could also compare PRAC with other mechanisms like graphing, para, or Hydra with a couple of sentences for a clear understanding of how PRAC performs in terms of security compared to other mechanisms, just similar to how they evaluate performance and energy consumption. Yeah, that's it. Thank you very much for your attention. And before we move on to discussion, I would be happy to answer any questions you may have.
So one of the questions I had was in one of the slides you show the how PRFM, PRAC fails, and that I want to know if the NBO for that figure was 100% of NRH or
So which slide do you refer to?
much further behind, much further behind.
Let me
Okay,
hear.
maybe here it's a good point to ask. So in these figures, is the NBO assumed to be equal to NRH? For instance, with respect to the wave attack, when the paper provides results about the wave attack, is the NBO assumed to be 100% of NRH? Because
No,
if it's not
no,
100% of the NRH, the wave attack should not cause any bit flips, right?
So the NIH is basically the threshold to enter the backup signal and issue the IFM command, right? And MBO is a minimum RowHammer count to induce the first bit flip. And if you have a much lower NIH value, and it means you will refresh the rows earlier, and it should ensure a higher security against the wave attack.
Okay, just to clarify, so NBO is the number of counts for the backoff signal, and NRH is the minimum row activation count to cause a bit.
No, NIH is a threshold to assert the backup signal, and MBO is a minimum hammer count.
Oh, okay.
Yeah.
Okay, thanks.
So maybe if you go to slide 56 or 57, it will be more clear, I guess. Yeah, if you explain this again, probably like everything will be clear about that question.
Okay, so basically, the wave attack just uses the delay period, and so because during the delay period, the memory chip is not allowed to assert a new backup signal, and while the activation count of the true target row is already near NIH, and during this delay period, you can just hammer the true target row, and its activation count is becomes quickly near MBO. And when it's over MBO and memory chip is not able to handle the true target row in time, then it causes bit flip.
Can you move on to the discussion points?
Yeah. Okay, so in evaluation, we discussed some weakness of PRAC, like incrementing timing parameters causes significant overhead, and PRAC is volatile to performance attacks and so on. So the first discussion point is how can we reduce timing parameters? And I will give you the first and the most effective direction, which is parallelizing row activations and counter incrementation. But how can we do it? And do you have any ideas?
Yeah. Can we move on to the next point? No. Oh,
No, I mean, we don't have any takers from the lecture hall, so maybe we can expand on the question.
Sorry.
So I'm saying we don't have any answers in the hall.
Yeah.
Yes, so maybe you can
Okay.
expand on the question. Yeah.
Okay, so if you do not have any ideas, so maybe one possible solution could be in current design, row activation counters are designed to be an extension of each row. And instead of doing that in this way, maybe we can decouple the counter from DRAM rows. That means we design a dedicated hardware and integrate it into DRAM. So this hardware should take the full responsibility of organizing row activation counters such that the counters can be incremented while a row is activated. But this will, of course, increase complexity and implementation overhead. And another possibility would be performing analysis to determine which rows are more volatile to RowHammer attacks. So that means instead of simply incrementing timing parameters in all cases, we can just increment it to those more dangerous rows. But in this case, the DRAM timing parameters need to be dynamic configurable instead of a uniform configuration. And also the analysis to find out which rows are dangerous could be quite difficult. Also, there's a technique called charge cache, which configures lower timing parameters for those rows, which are activated very frequently in short time. And the intuition behind it is in such a short time, the charge in capacitor leaks not that much, and there is no need to perform pre-charging. But this is a general solution for decreasing DRAM latency. But we can also use this technique with PRAC together to reduce overhead. But it does not decrease the specific latency introduced by PRAC. So that's why it's a general solution. And finally, PRAC can also benefit from the solar DRAM. It's also a general solution for decreasing DRAM latency, like charge cache. So DRAM has so-called strong cells and weak cells. Here, strong and weak basically means whether it can be accessed with reduced timing parameters or not. This variation arises from inherent physical variations in the manufacturing process of DRAM chips. So this mechanism can also be deployed with PRAC together to reduce the overhead. Besides, we also need to consider how to defend against performance attacks. And so remember, the performance attack depends on triggering many preventive refreshes. So do you have any ideas how to defend against performance attacks?
Maybe you can throttle or like have a counter at the memory controller, which counts the number of activations were performed at a bank level. And maybe that's not equal to like the row activation count, like the NRH, maybe some multiple of NRH, such that you can defend from wave attack as well as maybe performance attacks.
Mm-hmm. Yeah, that's a good point. And maybe some other ideas. Yeah, so I think the most simple solution would be accurately.
We have some ideas in the hall.
Okay, sorry.
Yeah, so first of all, I was sort of thinking about an attack, and I'm not sure if that works. So maybe you can give some input first. So is it possible that you increment the counters across many rows, basically, but you stay below the threshold, and then you can sort of trigger like a denial of service by just incrementing it once across many rows, for example. So is this a sort of attack that could happen?
So you mean bring the counter of all rows to near the threshold at the same time, and then you just activate all of them to launch an attack?
Yeah, for example, yeah.
That's possible. Yeah, that's
So
basically how wave attack works.
yeah,
You
so
basically
then
yeah.
so then
Yeah.
maybe to defend against this, one could try to detect such a pattern. So if you see an increase across all rows where the counters you try to detect these waves basically, and if that's the case, you sort of pause and reset or refresh.
Yeah, I think that's kind of a solution to wave attack. But here we are talking about performance attacks. So performance attack is quite simple. You just trigger many preventive refreshes. You don't want to induce a bit flip. You just want to use these preventive refreshes to block normal requests of DRAM.
Yeah, well, then I was misunderstanding the wave attack.
Okay.
Okay, maybe we can continue then.
Yeah. Okay, then. So I think the most simple solution is to accurately detect and throttle workloads that trigger too many preventive refreshes. And how can we do it? So for this, there is an existing mechanism called RowHammer, which is designed to reduce the performance and energy overhead caused by RowHammer mitigation techniques. It observes which hardware threats trigger a large number of RowHammer preventive actions, and then those threats are identified as suspect, and the memory bandwidth of them will be limited. And RowHammer is designed to work with existing RowHammer mitigation mechanisms, including PRAC, which means it can be directly deployed, and we don't need to care about integration and compatibility problems. But so RowHammer also has some downsides. For example, there is a possibility of false positives, which means memory-intensive applications could be identified as suspect by RowHammer and throttle, even they are not intentionally launching a performance attack. And also monitoring hardware threats could cause additional overhead. Yeah, that's it. And thank you very much for your attention.
Okay, let's close the session then. Yeah.
So thanks everyone and see you next week. So we also have some forms that you need to fill out some comments. I hope you're aware of those forms. So essentially there is one form that presenter, they can evaluate their mentors. So they can basically mention that if their mentor work well with them or no. And there are also another form that all the students can share feedback for the presenter. So make sure you attend to both because we will use both for this course. Thank you.